Brent Hilscher, process engineering for the last 15 years, Placerdome, Imperial Metals, some time at Syncrude, Hatch, and now I'm at SACRE-DAVEY, leading the mining group. We're doing a lot of ore sorting work, a lot of pre-crushing work, and a lot of updating the economics of feasibility studies with the changes that ore sorting makes to those studies. So today we're going to talk about sensor-based ore sorting and the change that has on project economics. 10 years ago, this was a pretty innovative, cutting-edge technology. Today, it's been proven in every metal and every type of mining application, and there's well over 50 mines using this. Some say over 100. So it's too late to be the first, which is fine because mining usually likes to have a bit of a race to be second to adopt a technology. Yeah, so it's too late to be second, but it's still time to be 51st. So we're going to look at the economic and technical impact that ore sorting has had on some of our clients' deposits. We've seen projects with a rate of return too low to attract investment get changed into very fundable projects. Mines that were losing money got turned around, and now they're going to be one of the most profitable mines in the company's portfolio. And the last 10 years have seen dozens of really amazing ore sorting projects happen. Most have been kept confidential because companies often see it as a competitive advantage for acquisitions and operations, which is completely fair. I'd do the same thing if I were them. So we really appreciate these 4 companies who have let us share some of their information. So ore sorting is now at a level of development that most engineers are surprised by. This is an example of an X-ray sorter. The rocks travel under the X-ray, are instantaneously assessed and tracked. Each particle, as it leaves the end of the belt, is hit by an air jet to divert it or let fall into the regular bin. Usually you divert whatever the lesser amount is. The stuff on the left there is about 15% of the mass, and that's the ore in this case. So that was diverted by air jet to save on air. So this company was able to eliminate 85% of their ore because 85% of their ore was not ore, it was waste, and they were losing money on every rock. The great news for them is 15% of their ore made all that waste rock collectively into ore. Throwing away the waste rock meant they made an awful lot more money by just processing the high grade. Also, it allowed them to no longer be mill limited. So they were able to, I think, more than double their metal production and still save on power and labor and maintenance. So here's some of the operations. This isn't by any means a comprehensive list. This is just some of our favorites. This is the sort of the new wave, the renaissance of ore sorting equipment. These are the high tonnage units. They are typically they're X-ray, X-ray transmission, X-ray fluorescence. There are still, color and laser and things like that. But the X-ray suite seems to be grabbing a larger market share every year. Also, this list is focused on hard rock mining, base metals, precious metals. We could probably double it if we were to include industrial minerals and things like that.
Any comment on the regionality? It's like Russia's very focused.
Oh yeah, and that's only a fraction of Russia's total. In terms of ore sorting, I'd bet Russia's the world leader. I haven't done a study, but it looks like most of their operations, for gold at least, use it. and they tend to use XRF. Yeah.
Brent, good to see you again.
Yeah.
We're sitting in Canada, and obviously Canada's quite thin on that list. Any thoughts about why we're not taking this technology up?
So why isn't Canada on the list is the question. Answer is mining is slow to adopt new technologies. Canada will be on the list. We're actually building one right now in British Columbia, a gold mine. Full-scale production unit. It'll be finished by the end of the year for sure. So then we can set up tours for anyone who wants to go visit. Yeah.
The driving force for this, is it mining techniques and dilution, or is it the nature of the ore body?
It's both. So the question is it dilution or is it internal to the ore body? Mainly we focus on the ore body. So set aside dilution. We look at the ore and how variable is that ore, how many waste rocks are in that ore. Dilution is a nice little bonus for this business case, because if you can sort the ore from itself, the dilution is even easier because it has much different characteristics and typically even lower grades, so it's a very sharp separation. So hopefully we'll add some Canadian gold by the end of the year, and also some Mexican silver too. So some clarity is SACRE-DAVEY is not an equipment supplier. We don't make equipment, we don't sell equipment. We're an engineering company. We manage the testing, the design, EPCM, and sometimes EPC if it's less than 100 million. And of course we look at all the technologies. So we work with all vendors. There's over 10 of them. Steinert, Tomra, MineSense, RedWave, Rados, and they're all very good. They've all been advancing very, very quickly. A lot of them have doubled their tonnage every 2 years. So it's very much matching the right sensor and the right manufacturer with a specific project geology. And you can't say, well, this gold mine worked with this sensor, so this one will too. Sometimes that happens, but it's almost always a coincidence. You got to do the test work. So that's where we come in.
So it depends on the sensor?
It depends on the geology. So what is the gold associated with it?
Dictates the sensor?
Geology dictates the sensor, yeah. And the cost?
I heard you about the cost yet.
The cost? Cost varies dramatically. XRF is one of the most expensive. Optical is one of the cheapest. It's pretty tough to say. Usually the cost of the equipment itself is pretty insignificant compared to the total cost of the project, which is usually fairly insignificant compared to the revenue increase. Usually we shoot for about a 4 to 6 month payback on a brownfield expansion. If we're doing a greenfield project, we don't need to worry about payback because putting in ore sorting allows for a smaller mill, and then you save on your total capex, so it's not an issue then. So mining's faced some pretty real challenges in the last few years. We've got declining ore grades, increasing energy costs, labor cost, some stagnant metal prices in cases. Investors are only now investing in projects with very high rates of return. This makes greenfield projects a little more challenging, and brownfield operations are also feeling the pressure to increase revenue without spending dramatic amounts of capex. But if we can improve the mill feed grade, a typical result we see is we double it. So if we can double the mill feed grade, these challenges start to become much more manageable. You can have your unit energy costs, have your labor cost, have your tailings pond size relative to metal production. These are all really game-changing concepts. And the best of all is if you've already got your mill built and you double your mill feed grade, you can double your revenue. And so that's not doubling your profit. You can double the revenue. So all that extra revenue just adds to your profit. So it can be quite dramatic.
Brent, can you
Yeah.
apply this to a heap leach?
Generally, we don't. Heap leach grades tend to be so low that it starts to get
Undetectable?
tricky, whether it's worth the extra, well, it's an extra $1 a ton.
You're sorting for $1 a ton?
Hmm?
You are sorting for
Yeah.
$1 a ton?
That's right. Plus handling charges, so that might be another, it depends on the operation and tonnage, but might be another $1 a ton.
It might be a convenient place to put into an existing conveyor and it's almost nothing, or you're building a whole sorting plant, it's $50 million for your plant, you know, depends on geometry.
Not the way we build them, but yeah, it could be, yeah. Yeah.
Depends on how big it
Yeah,
is.
yeah. We have looked at heap leaches before. Typically, the opportunity is you've got bimodal distribution of gold grades. So most of the ore deserves to go to the heap leach, but then there's a percentage of ore that's has different characteristics and would be worth milling if you had a way of diverting it. And an ore sorter can be an excellent way of doing that. And diverting that high grade, anything over 2 or 3 grams per ton, to a special processing facility.
Could you do that, for example, separating sulfides from oxides?
Yes,
Take the sulfide fraction out of your
Yeah.
stream?
yeah, yeah, that's been done. It's tricky, but it's been done.
$1 a ton, but I don't quite understand it. If you're going to double your yield or your production of gold, then don't you have to double your mining rate?
Yeah, yeah, yeah.
The mining rate is less than $1 a ton, including the sorting.
Oh my, no. No, this is just the sorting
You
costs.
said you can double your revenue.
Oh, if you want a whole project cost thing,
I do.
I'll have to charge you for that. Yeah, it gets complicated if you're underground. A lot of times,
I'm
open pit?
The question from Bob or Rob about using heap leach.
heap leach, yeah, the price will go up.
And is there actually an operation where this is being done that
Oh,
you can
yeah,
source
yeah.
between heap leaching and with or without ore sorting?
Let's see, we've got some waste, a lot of waste rock.
That's rock already gone mined.
Yeah, these are all, they mine the rock and then they either take the waste, sort the waste, or they take the ore and sort the ore.
Do not charge except for reclaiming the rock.
Hmm?
Well, you say they take the rock.
Yes.
Presumably this is old rock, previously mined rock, which has been written off.
You could, that's called waste sorting.
Oh, no,
So you can take the waste, sort your waste piles, take the high grade out of that, that's very common. You can also take your live ore, intercept it after your gyratory, and process it on the way to the mill. And they're both very good applications.
sorting, but the costs are very dictate the choices.
Yes, yeah.
Much more. You
Yeah.
said the sensor isn't more than 10% of the cost. It's the sorting of the belt, the cost of the air compressor. That is 70% of the cost.
Yeah, that's why you get up to $1 a ton. Otherwise, it'd be 10 cents a ton. But that air, it's expensive. Although the cost of the air compressor it pales in comparison to the cost of your SAG mill and your ball mills. So if you can divert half of your ore, and it costs $1 a ton to do that, you save a lot of money still.
The heap leach.
Yeah.
Which is
What kind of tonnages you got up to? A few hundred ton an hour, 1,000 ton an hour?
Well, it depends. You've got a suite of different technologies, and we deal with all of them. So we do screening and heavy media. That's not really covered here, but you've got almost unlimited tonnage with those. You've got the MineSense technology, which is shovel-based. Again, that's almost, as you scoop, it goes. You've got conveyor diverters, unlimited. Unlimited. Not these conveyor diverters. These are rock by rock. So the conveyors we're talking about is a standard conveyor piled deep with rocks, fines, the whole mix. and you scan through the entire belt using prompt neutron activation, something like that, and divert all of it at once. It's not very selective, but it is incredibly high tonnage. Once you get into things like the video we saw, rock by rock diversion, your limit's about 300 tons per hour, theoretical maximum, per machine. We've got one client was going to do 200,000 tons per day. So that requires a 32 pack approximately. It's also very sensitive to the technology that's used and the size distribution of the rocks. The finer the rocks, the less capacity each machine will have.
Okay, thank you.
No problem. So it's a bit of a Swiss Army knife. It can do a lot of different things, not necessarily all at the same time though. It can increase the mill feed grade. It can increase the resource by lowering the cutoff grade for the mine. It can take waste and turn that into ore, which is basically the same thing as lowering the cutoff grade. It can take old waste piles and create ore out of them. The fastest payback business cases are usually sorting the mill feed, because double the revenue and everything is happy. But there are a lot of other things it can do. We're also building a project right now that is looking into sorting sulfides out of a waste pile so they can produce non-acid generating waste piles.
The fastest return actually occurs in industrial minerals. Where you take waste pile that's been there and you remove some black rocks from it and you make something with value that's $400, $500 a ton. And
Yep.
creates real estate around the mine site.
Yep, that'd be nice.
In Europe this is very important.
Yep.
But, that's why you find far more examples in the industrial minerals than
Yep.
in the metallic mines.
Yeah, and even more so in recycling, which is where the
Recycling,
current
yeah.
suite of
There's
technologies have
economics
come
of
from.
recycling. It's all government.
Yeah. So a lot of this comes down to heterogeneity. How variable is the ore zone? A lot of projects say, oh, no, our block models, all the grades are the same. We've looked at projects like that where the blocks are indeed very, very similar to each other. There's not a lot of natural variation in those. But when you get down to the 4-inch level, there's tremendous variation. And you look at the distribution of the ore grade, and half of the rocks in that uniform ore body are far enough below cutoff grade that the mill loses money when they process them. Yeah.
Yeah, Brent, that's a very, very good point. Has this technology been applied into, say, metallurgical testing at the preliminary economic assessment stage or pre-fees?
Yep.
And built into models?
Yep.
A lot of your examples tend to be post-built.
Yeah, that's what we're doing now. So we've had about 10 projects where we've taken the test work and incorporated it into a design and into a new feasibility study.
Well, buy a model that allows you to insert ore sorting in a mine layout or building a mine. There isn't. The industry hasn't produced that yet.
And do you ever do a comparison with the DMS?
So the question was, do we compare to DMS? Yeah, we've done quite a few comparisons.
Student metallurgist acronym, but DMS is.
Dense media cyclones.
Okay, thanks.
And actually, I'll talk about that a little bit in the XRT section. But so we look at DMS as complementary technology. Ore sorting works down to 1/2 inch is pretty much the limit. You can go a little finer, but the machine costs start to exponentially increase. But that's right around where dense media cyclones start to pick up in effectiveness. So we will look at this and say, all right, it's sortable by XRT. we'll take the coarse material, sort it by XRT. It's more selective because it doesn't look at the average particle density. It looks at the density profile. So the average density could be low, but 5% of that rock might be in the target density profile range. And the sensor can say, well, yeah, it's a low density rock, but 5% here, this little crescent, looks like ore. And we know that ore is valuable enough to make that whole rock worth processing, so they'll take that whole rock and send it to the ore bin. Whereas a DMS can't do that.
I just changed the rules. A lot of your questions will be answered in the presentation, so let's let him get a little and then we'll see what he doesn't cover.
And sorry for the coughing. The doctor says it's not contagious, so you're all safe. So don't feel bad about not knowing the heterogeneity of your deposit. No one's ever measured it at the 4-inch scale before because it's never mattered before. There's been nothing useful you could do with that information before, but now there is. So now we're starting to measure this. And the more variable your rocks, the higher the potential for ore sorting. The higher grade and lower grade, the better the potential. If we can throw away rocks that are absolutely barren, that's the best case scenario. So this is the state of the art here. This is actually in Japan. They still do hand sorting. It's one of the rare cases where Russia is ahead of Japan in technology. Below is the 32-pack that we're thinking about for one of our clients who needs, they have an open pit, 200,000 tons per day. But usually you'd look at that and say, okay, well, let's try mine sense and the conveyor sorting. But in this case, rock by rock sorting was very, very effective. And their ore is valuable enough that it's worth sorting rock by rock in order to maintain that very high recovery and also produce a very high concentrate grade. And in this case, they saved, I think it was $600 million by spending the extra bit for the ore sorting plant and then making their mill half the size. All right, so here we get into the technical part of the presentation. XRT is usually dual energy X-ray transmission. That compensates for the size of the rock and gives you the density reading instead of just the absorption of it. It's able to measure the density profile, which is wonderful because you're not just looking at the average, you're looking at a statistical distribution of density in that rock. Of course, this is all happening to hundreds of rocks at the same time, but processing power is now more than up to the challenge. 10 years ago, it wasn't, which is probably why in the 90s these machines were focused on diamonds and small tonnage operations and things like that. Here's a video of my last trip to Germany. Steinert and Tomra both have manufacturing and labs there. This was taken with my iPhone. And I think this lies. This isn't XRT, this is actually laser sorting. Very noisy. Yeah. Not sag mill noisy, but noisy enough. With this model, we were looking at taking some rubber belting and bolting it to the back wall. Most of the noise is from the rocks being projected into the steel plate and then dropping down. Yeah. In this case, the ore represented 35% of the feed. It was a silver project we were working on for one of our clients. And you see it, this has no problem dealing with high speeds. This is moving at over 2 meters per second. I think it's 2.6 meters per second, which is how they achieve the tonnages of 200 tons per hour.
How much difference in grade between the reject and what you call ore?
Oh, the difference between is pretty huge. Usually we look at the difference between the feed and the final product. In this case, it was about triple, which is a little out of the ordinary. Usually double is what we shoot for. Anything over 25% mill feed upgrade is considered a success, assuming you don't lose too much metal in doing that.
It's a very good average figure to remember. 35% yield for double the grade.
Yeah. I wouldn't remember that number because every deposit is completely different.
Absolutely.
Yeah.
If you average all of them out, that's what you get.
Yeah. How tall is a building? Well, they average this, but it's not very helpful. So your question was? Recovery. Again, that varies. Well, this might be a good time for the recovery. So that's based on the economic model. You can't say what the best recovery is or what the best upgrade ratio is based on gut feeling. You have to have all the mine capex, opex, the mill capex, opex, put it all into a very simple economic model so that you can also input the grade recovery curves and try a few scenarios. And then you can go to them and say, look, 90% recovery is what we want. Oh, but you can get 97. We can get 97, but 90 is the best because here's your upgrade ratio. You're throwing away more worthless rocks, and this is going to get you your best rate of return and best net present value, and that's why you want to do that.
It's the same as any grade recovery
Yeah.
analysis that when you do, mass pull on your flotation, it's the same
Yeah,
analysis.
yeah. And then we can say, look, we can get you your recovery higher again. How much money do you want to waste processing rocks to boost your recovery statistics? And usually they'll say, oh, no, it's fine. Leave it the way it is. So in some instances, density of individual rocks might not be helpful in sorting. A lot of times if you're dealing with a medium density material, you might have barite in your ore, which is very heavy. Trying to separate sulfides from quartz and barite can be tricky because a little bit of quartz mixed with a little bit of barite sometimes looks like sulfides. In those cases, XRF is incredibly handy. It gives us a surface scan of the material, kind of like an assay. It'll give you a number of counts, and that'll let you determine your metal content in the ore. It's surprisingly accurate. Very rarely do we find copper hiding in the middle of the rock somehow. Usually the scan will show a reading, and it's usually well within the statistical error that we need to determine, is this rock worth throwing away or is it worth keeping? And errors made are usually errors made with those marginal rocks that might be worth a tiny bit if you processed, but if you lose them, no one's too upset by that. This is an example of a, let's see, this is a, gold mine that used copper, zinc, titanium, and iron as indicators of the presence of gold. So we don't scan for gold directly, no one does yet, but that has never been a problem with most of the operations yet because gold doesn't get deposited by itself. It always takes other things with it. In this case, copper, zinc, titanium, and iron. Also, a lot of times we'll find negative correlations, so zirconium might be in the waste rock and not in the gold-bearing rock, in which case we can use that as a negative correlation just as easily. So in this case it says, this has 4 grams per ton, it's worth $160 per ton, therefore it's ore, and we keep it. Color, infrared, ultraviolet, all very common technologies too. They require a clean rock. Electromagnetic. Haven't quite found a deposit that needs this yet. If you've got magnetite associations, if you've got coherent veins of pyrrhotite, it might be handy. We've tested it a few times though. Getting into the cutting edge now, if people really did want to be on the cutting edge, we have laser-induced breakdown spectroscopy. So we shoot a high-powered laser at the rock, vaporize some of it, superheat the vaporized rock into plasma, and then as it cools, we look at the spectrum, and it gives us our metal content. Well, not just metals, it gives us all the elements. So very handy if you've got a lithium mine and you don't want to use a color sorter. You would be able to measure it directly. Might be a couple years away from production yet, though. So this is the MindSense technology, which is fairly new still. There have been a few places around the world that have tested this, and the results seem to be quite positive. As the ore falls into the bucket, the sensor sweeps it, so it's not point analysis, it's a sweep. Takes the average, and a little red light or a green light pops up on their dashboard saying, this bucket is ore, this one is waste. You can then put it into a ore truck or a waste truck. Alternately, you could use the same truck as you always use and average the 3 scoops that go into that truck and say, all right, this truck is now going to the waste pile. It would be very handy, especially to have on the trucks that were scooping up waste. Because every now and then, everyone knows you get a couple pockets of good stuff in your waste piles. If that truck could be diverted to the mill, that would be a significant amount of metal. And yeah, it would be basically free. So the 80-20 rule applies to many of the existing waste piles. 20% of the rocks often contain 80% of the metal. Sometimes it's 90 to 10. By removing the fraction of valuable rocks, you can often create an ore that's much, much higher than your feed grade. The limit is the geology. There is no real uplift ratio limit to ore sorting. It depends on what are the grades of the good rocks once you take away everything else. And once you start processing your waste piles or waste stopes for profit, the geologists like to turn those into resources, and that makes everyone happy. These are some of the suppliers and labs that we work with. Rados are the ones in Russia. They've got a very, very sensitive machine, very accurate. Steinert, Tomra make very large machines, able to sort rock by rock. MindSense, of course, has the shovel. And then there's a number of others, Red Wave and various conveyor belt diversion sorting mechanisms and things like that. And it's nice being an engineering company because we can deal with all of them and pick which one is right for a specific deposit. This is typically how we'll configure the flow sheet. It's nice to have a gyratory first. It's not absolutely required. What is required is getting in the right screen size range. So 1/2 inch to 4 inch tends to be the sortable rock by rock range. If you're going with conveyor diversions or shovel, of course this wouldn't apply. This is just for the rock by rock. So you get your size fraction, you send that to the ore sorter, that rejects, and then the fines and the ore sorter product are recombined and sent to the mill. If you've got a high tonnage operation, more than 300 tons per hour, it often makes sense to put in a couple ore sorters and then differentiate, have one on a finer fraction and one on a coarser fraction. Anything you can do to keep that particle size distribution ratios as tight as you can. All right, so here's some of the examples we promised. Operation A is an example of waste sorting. Here we're able to get 63% of the waste metal into an ore grade above cutoff. With waste sorting, we usually like to see a 5-to-1 to 10-to-1 upgrade ratio. because of course you're starting with waste. But in this case, the geology wasn't really cooperating. Nevertheless, we did create ore out of a waste pile. And after we did all the expenses, CapEx, OpEx, looks like the ore produced would pay off the sorting capital expenses in about 12 months, which is not usually what we like to see. We usually like to see 6 months, because in today's capital market, most major companies say if we give you $1 in January, we want $2 by December. And usually that's achievable. This wasn't the best example, but we wanted to show the whole range. So some of the other examples will be a little more impressive. So this was a American underground silver mine where we needed to take a fairly high-grade silver ore and upgrade it sufficiently to justify trucking it a long distance to be toll mined. So very small tonnage. The sorting algorithm used zinc, iron, titanium, and zirconium to predict the silver grades. We tried a few different cutoff grades for the ore sorting equipment. We got a 40% boost in ore grade for just about a 1% loss of recovery, which is very nice. If we took a 20% loss in silver, that led to a 300% increase. This was our first ore sorting project, so we didn't actually build the economic model. So we weren't able to recommend which of these scenarios was the right one for them. We learned our lesson there, so now we always do an economic model with every project. Otherwise, how do you say which of these is the right one? And if we went all the way to the top 5% of rocks, 46% of the silver was contained in just 5 out of 100 rocks. And although we didn't do the project economics for this one, these guys' stock has tripled since this report came out, so they seem to be doing just fine.
You promise that with every company?
I do not promise that. All right, so this was a large US-based polymetallic project. They needed to boost their rate of return, to boost investor interest. They also needed to cut their CapEx to make it the investment size a little more reasonable. By rejecting half of the mill feed, the mill size was halved. So all the CapEx associated with the mill was reduced by the appropriate percentage. You can't half the CapEx, but significantly less. I think it was around 40% less. Also, the tailings pond was halved. Half the tonnage going through the mill means your tailings pond is half, and that was a huge, huge cost for them. In the end, even though I think this cost around $100 million to set up the ore sorting plant, they saved $700 million in other costs. And I think they increased their metal production a little bit. Also, they were able to reduce their production costs because now, smaller mill, less power, less reagents, less everything. And mine D, this was a silver mine slated to be shut down. They had far too much dilution, except it wasn't actually dilution. Their ore blocks, when you did the scan, what was it? Around 80% of them were worthless. So they were losing money on most of the rocks that were going into their mill. So it was very easy. We say, well, stop processing all those rocks and you'll stop losing money. This mine is now set to become very profitable, and they're very, very happy. The mine is going to have to do a little work to catch up now because the mill is saying, okay, can you quadruple our feed rate? And the mine's saying, no, we can't. We can maybe double it. But still, if the mine can double their production, now you've got twice as much silver and the mill's still underfed. So you either run at reduced capacity, shut down one of the circuits, save on power, save on labor. It's still a definite win for them. Their profit went from minus 3 million to somewhere in the 50 million range. Here's a bonus slide with some a gold mine that we did, and Kensington Mine. I can mention the name because it's not one of my clients and their information is public. They did a waste sorting project where they increased their waste pile grade almost 10 times, about 8 times it looks like, and produced a fairly clean waste pile. 61% recovery, not terribly impressive until you look at the upgrade ratio and the amount of money that they're making on that waste pile. And then that is actually pretty impressive. They took something that was worthless and now they're making money on 61% of it. All right, just wrapping up here. How we usually test this. Every site is different. All the results at every site are always, always different. You can't say, the guys down the road got this result, so will we. It never works that way. Each site needs specific testing. Typically, we'll do 100 rocks per deposit for a scoping study. Pre-fees will be 100 rocks per zone, especially if the zones have differences in gold associations at all. Rock by rock analysis is very, very important. Especially with gold, platinum, silver, you want to have the association and the algorithm between all your indication readings, be it XRT, XRF, color laser, and the gold content. So and then you can do simulations on what the sorter would have done. Once you can also put it into your economic model with those grade recovery curves. Once you've built the economic models, you take the best economic models, put them into the bulk sorting stage where you prove them using a more representative sample. That takes us to feasibility level of design. Usually people avoid the pilot plant because it'll often cost almost as much as a full plant. But 50 tons can be tested easily enough in most of the labs. So most of the lab equipment is full-scale equipment. So, conclusions. Ore sorting is now a very proven technology. You don't have to worry about being cutting edge with most of these technologies. It's too late for that. It's been proven all around the world. There are still emerging technologies that if you do want to be on the cutting edge, there's quite a few of them. LIBS is a good example of that. Ore sorting can reduce your haulage, lengthen mine life by pulling ore out of waste piles and lowering mine cutoff grades. Sorting revitalizes greenfield projects by reducing the CapEx and OpEx. Besides reducing capital and operating costs, it also reduces the environmental footprint. So your CO2 footprint, your water usage, your tailings ponds are all reduced. That has a definite benefit with government and community relations, which shouldn't be underestimated. If anyone has any questions, I'd be happy to answer them now or after the rest of the talks.